La.
Orderly. It's here. So I'm not sure whether this should go on. Because this is a micro. So I think I was told to switch off that one here. Or not. Then this is automatic here. So can people on Zoom hear me? Maybe some reaction? Oh. Yeah. Thank you. I hope everything is okay. I shouldn't move this. What does this say? Now. Okay, better is good. Just okay. It's about subtitle. I think we can start. Thank you. This will be enough. Okay, let's continue. So we are still in chapter 1, and we will not get beyond chapter 1 today, and also not in the first part next week. We are at section 1.5 functors, and I said yesterday there are 12 sections, but actually there are 13. So the last thing we did was defining what is the equivalence of categories, where we had these natural transformations between the identity functor on one category and the composition of two functors on the same. Going from that category to the other and back. And one goes in starts with the identity of one of the categories, and the other one ends at the identity of the other category. And we call also then the two functors that we have which make up the equivalence quasi-inverse to each other. And the first thing maybe to add here is a remark. There is what is called the principle of equivalence. So we could also introduce, it exists, the notion of isomorphism between categories, where we have a bijection between objects and morphisms. But I already pointed out that it's typically not a good idea to say that objects are equal, but only isomorphic, even though very often we have to keep track of the isomorphisms. So it's more sensible to say that two categories are equivalent, meaning in particular that they can have different numbers of objects, but they will have, one aspect is they will have the same number of isomorphism classes of objects. And the principle of equivalence says that good, I don't write it in words, it's very simple. It says that when we want to make statements about categories, the properties of class of categories, and what the value of some quantity is for a given category, then typically it's not interesting to use quantities which are different for two categories which are equivalent but not equal. So interesting properties will take the same value for categories which are equivalent. So maybe I write anyhow good properties invariant under equivalence. Let me put it like that. So, for example, good properties are
good properties.
We should use that time. Is this a question or?
I think he just repeats one, two.
Okay. So example for quantity is the number of isomorphism classes. And to save space, I just write iso classes. So equivalent categories will have the same number of isomorphism classes of objects. And then also the number of path components. Remember, I denote this by pi 0. But a bad property would
You can mute everybody.
Yeah. 28. Maybe I continue meanwhile. So number of objects would be a bad aspect of a category. Typically, we cannot even talk about the number because there will be infinitely many objects, even if you have just one isomorphism class. We could infinitely many objects. More important, maybe because it's important, starting your column here, is the following proposition, which is a criterion for having an equivalence. It says that a functor f from C to D is an equivalence if and only if two properties of f are given. First, f is essentially surjective. That means if we have any x in D, then there is a say V in C such that x is f of V. No, not true. Isomorphic to that. Isomorphic in D, of course. And the second is that f is fully faithful. Which means that for every pair, say V and V prime in C, we have that the map, which we again call F, remember, from the morphisms which have source V in charge of V prime to the morphisms in D, which have charge F of V and source F of V charge F of V prime, that this is bijective. And the nice thing about this is that both of these properties are very often easy to check. So, and I do not get a proof. We give a proof. Maybe just some comment. There is, well, of course, you find this in many places. In every book about category theory, but there's one book by Cassel on quantum groups. I think it's just called quantum groups. I have not yet prepared the list of references on page 278. And what you do is say you have a functor f which has these properties, and then using these properties, you construct the unit eta and co-unit epsilon of your of the equivalence, and on the other hand, if you have the equivalence, no, so when you have the equivalence, you use the unit and co-unit to show that the functors have these properties. And just as a side remark here, you when doing that, you actually invoke the axiom of choice. That is usually not mentioned. And in all I will do in this course, I will at least tacitly always assume that the axiom of choice is valid. Some terminology. We say that the category C is essentially small. If and only if it's equivalent to a small category. So actually, small category is a kind of nice property, but it's not a really good one in this sense. What is a good one is essentially small. And indeed, very often when we in an argument assume that the category is small, then in many cases we can extend the argument to essentially small categories. And then a skeletal category. This is a category where in each isomorphism class you have only one object. So if you have X and Y in C, then actually they are equal. And it's in conflict with what I said about what is nice to talk about such categories, but for some arguments, you actually restrict your attention in the first place to skeletal categories and then wire equivalent extensions. And then also, once you have this, you say you have a skeleton of a category C. This is a subcategory which is skeletal. And such that the induction functor is an equivalence. The inclusion functor. I wrote induction here. This is nonsense. But this simply means that you pick, again, using axiom of choice, you pick in each equivalence isomorphism class of objects, just one object, and for some aspects or in some proofs, this is sensible. Just like say in linear algebra, it's not very natural to choose bases for your vector spaces, but for some proofs it's very convenient. And again, via the axiom of choice, it's clear that every category has a skeleton. So when we want to make statements about categories, sometimes implicitly we go to a skeleton. And then finally, I should add this here. We say that C is essentially finite. And this is a category which is equivalent to the finite category, where finite is in the sense that there are finitely many objects, finitely many the set of morphisms is finite. And as a consequence, the set of objects is also finite. So equivalent to a finite category. And I don't write the definition of finite. It's rather clear. Now we come to the next section, and this is slightly more advanced. And in the very first introduction, one would not talk about these things. But well, at some point, have to mention them, or at least implicitly work with them. I will do this in some detail, and the major reason for doing that is that I want to give a definition of what is an abelian, and more generally what is an additive category, and to get a convenient definition of that, it's nice to use the notions of limits and co-limits. And actually, this needs quite a bit of preparation. So this this section is not very short. And we first need need the following definition. Let I be a small category and C a category, then a diagram. This is a new use of the word diagram in C of shape I. It's just another word for a functor from I to C, and we call this functor for convenience, for later convenience, X or something similar. And you could ask, why do I need this concept? Well, I need it because I will define limits and co-limits in terms of this concept, and I need limits and co-limits for a lot more things. Let me give a simple example. Where the index category, that's what I stands for, is actually finite. It would be 156. Let's say there are just three objects, which I call a dot and star and something else. And there are just two non-identity morphisms. These are the identities, and then we have a morphism which I call alpha, which goes between these two objects, and the morphism I call beta, which goes between these two objects. And then we can just illustrate this as really saying we have these three objects, and then we have these morphisms alpha and beta. And then the diagram of shape I in an arbitrary category C is it's a functor, but we can draw it in the same way as this diagram. So there are we need three objects, say Q, R, and S. So the diagram is three objects, Q, R, S, where Q is the so it's called the diagram X again. Q is X of the first object, R is X applied to the next one, and so on. And then we need two morphisms, F and G, which are obtained by applying X to alpha and beta. And they are here. So this looks very boring, and in itself it is boring. I will give another example, which also does not look too interesting, but which is of definite relevance for us. Introduces some notation which we will need later. 157, another example, or class of examples. We define the following. Assume we have an object X in C, and then we introduce a functor, which we call a constant functor. And we note it by delta. or if we want to specify our object x by delta x. From I is a small category as before to C. So this is a diagram in the sense defined here, which maps any object I to the specific object x in C, and which maps any morphism in I to the identity of x. So there's a good reason to call it a constant function. This does the same to everything. And this generalizes as follows. We call, first an intermediate step, the binary diagonal functor. Which I just call delta, which goes from the category to the Cartesian product of the category itself, and which just maps every object to the pair consisting of twice the same object, and analogously for morphisms. And then, so here we do not talk about any I. This would be actually a very special choice of indexing category. And then we have something we just call the diagonal functor, where we now have some I, a small category, and then we call this delta I. And this goes from C to the category of functors, from I to C, well, to the category of diagrams. Diagrams are functors, therefore I can define a morphism of diagram to be a natural transformation between them as functors. And it does the following. If I take an object in C, it maps it to this diagonal, to the constant functor delta x. And if I have a morphism, then this has to be sent to a, say, from x to y. This has to be a natural transformation from delta x to delta y. And it's defined as eta I. So this would be the component of the natural transformation eta at the object I in the indexing category I. This is just given by F. So all the components are equal. And now I use this to define what I call a limit, two steps. We assume that we have a diagram of in C of shape I, and then we say the cone to X to this diagram is an object Y in C together with a natural transformation. Call it alpha, which goes from the constant functor delta I to the functor which is given by the diagram. And of course, the constant functor in particular is also a diagram. So what does this mean? Maybe I write it here briefly. So alpha is a natural transformation. So it's a collection of morphisms alpha I in C for every I in I. And so this goes from Y to X of I. because on this side we have the constant functor, so we always have the same object y, and then it has to be a natural transformation. If you insert the definition of natural transformation, it just reads that for all ij in I, we have that alpha j is the same as x of f after alpha I, when f is a morphism in I, which goes from I to j. And then we say a limit of x is a cone. Let's call it y and alpha. So alpha goes from y to x. Delta y to x. Such that for any other cone of the same type, so let's call it theta and natural transformation beta from delta theta to x. There is a unique transformation morphism, call it phi from z to y, such that this connects the two natural transformations alpha and beta, only alpha combined in the only way that makes sense. No, in one of the two ways that makes sense, alpha composed with phi is equal to beta. And this type of property that you have an object or something with a certain property, and it for any other, in this case cone with the same thing with the same property, there's a unique morphism between them. There exists a unique morphism. You call this a universal property, and we will have to deal with various universal properties later on. So the limit is something defined by a universal property. Maybe before I continue, a warning. One often says that y is the limit, but a limit is really a pair, an object together with a natural transformation. And in some situations, the natural transformation is rather obvious, and one does not talk about it. Remember, we have the notion of opposite category. And I mentioned that whenever we have an interesting notion for categories, by translating or doing the same for the opposite category, we get something new or dual in the original category. And if we do this here, then we get a definition of what is not a cone, but a cocone. Cocone to X is again an object in C and a natural transformation. But now, since we are in the opposite, this is why the opposite, or we should think in terms of the opposite category, this goes in the other direction. And if we do this explicitly, then again, we have a collection of morphisms alpha I, which now go from x I to y, such that alpha j is given, alpha j composed with f of x is equal to alpha I for any f from I to js. And then a co-limit of the diagram X is a cocone, with again a universal property such that for any other cocone there is unique morphism, and now in the other direction, such that, and now here again, it's that I call it psi now to have different formulas. So psi goes from y to z, and we have psi composed of alpha is equal to beta. Let me give you a trivial example, namely in the case of this example here. What is a cone in this situation? So we use everything that we had done in this previous example, and then a cone to this to the diagram X, which I have described here, is an object. Let's call it P in C, together with, and now I use a different letter here, just two morphisms. Pi Q and pi S, which go from P to Q, respectively P to S, such that if I insert them into this diagram here, P to Q, so pi Q here, P to S, so we have pi S here, and then this diagram commutes. And this is more or less automatic. If you look at the definition, then you have to give three morphisms, namely pi Q, pi S, and pi R. So from P to R, but you have, by definition, you need that for these morphisms, which I call F and G. It has to be true for all morphisms which are X of, well, all morphisms which are X of a morphism in the index category. By definition, we have the requirement that F composed with PQ is pi Q is pi R, and G composed with pi S is equal to pi R. But pi R is equal to pi R, so F composed with pi Q is the same as G to be composed with pi S, and this simply says that this diagram commutes. And so the information in this pi R in this case is just redundant. And then in this situation, what does the universal property look like? So the cone is a morphism such that this commutes, and if I have any P prime, with morphisms probably also prime, PQ prime and PS prime, such that this outer diagram commutes, there is uniquely a morphism. This is the one we have been calling phi, such that in this complete whole diagram, all the sub-diagrams are commutative. Now, this is a very special type of limit, but it's an important one. think I can take away the definition. General. So therefore it gets a name of its own. Of we just write type 161. So of the type that I described here is called a pullback. Which is a name that makes sense. We start with this yellow diagram and somehow we pull back the information to a single object here. Of course, it's not just an object, it's object together with this natural transformation. And dually, if you look at the co-limit of a diagram, of the shape that we have, we just take this and invert all arrows, and I draw it slightly differently. This is called push out. And again, what is it? It is an object X, Y, Z, say U, together with morphisms here, such that this commutes. And if there's any other U prime, well, natural transformation with corresponding components here, such that the big diagram commutes, then there is a unique morphism now from U to U prime, such that the subdiagrams commute. And there's also special notation for this. In the case of a pullback, maybe I write this. We write this P as X cross over, no, like change notation, Q cross over R S, and here we would correspondingly one writes the U as X, and then a cup symbol over Y Z. And then already over, no, I'm at 5 minutes more. Okay. An important result, which is analogous to many other results where what deals with universal properties, is that in general, a limit of a diagram need not exist. For such simple diagrams, very often it's easy to see whether they exist or not, but in more complicated situations, it can be hard to decide. So it's important to know that a limit of a diagram, provided it exists, is unique. And the same is then true also for a co-limit. Unique, as usual, not on the nose, but up to canonical isomorphism. So if I have two of them, say y and y prime, then there are two corresponding natural transformations alpha from y to x and from y prime to x. And then there is a unique phi from y to y prime, or I could interchange their roles such that alpha prime composed with phi. And actually, the fact that you can exchange the role of y and y prime here, obviously, is also the key ingredient of, or one key ingredient of the proof. If you look at the universal property, then so this would now be my y, and this my y prime. Then I get such a phi from the universal property. On the other hand, if I exchange the roles of y and y prime, I would have y prime here and y here. Using again the universal property, I get a morphism in the opposite direction. And then you have to check that when you compose them, actually you get the identity. And definition is no longer here, but when I define limit and co-limit, I said L limit and L co-limit. Since essentially the limit is unique, one often just says the limit. So when one says the limit is y, then one means it's y together with a natural transformation alpha up to such isomorphisms phi satisfying this property. And the question whether limits or co-limits exist is can be hard to answer, but one can make a lot of statements for all categories which have limits and co-limits. And that means if for a given category, I can decide whether this is true or not, then I have a whole bunch of statements. So therefore, one defines C, a category is complete. Definition if all limits exist. Meaning, if I take any small category I take any diagram of shape I in C, then that diagram has a limit. And of course, that's the dual notion. C is called co-complete if all co-limits exist, and then one also, in some case, one does not have all limits, but one still has all limits for the case that the indexing category is finite, and then one says it's finitely complete or co-complete if all finite limits or co-limits exist. And that's a good point for practice. Open the doors. Oxygen. Do you have any questions?
Well, where to motivate the main limit from topology? We formulate the topology.
Limits in some situations are limits in this categorical sense. But you have to be careful sometimes you are traditionally something a limit, which is actually coding. So if I'm not mistaken, then if you have a directed system, then a limit is a limit, and then inverse limit is a co-limit, but it could be the other way around.
So what's the motivation of defining the limit and co-limit?
We will see that we need this, or it's very convenient to have it for the definition of additives and abelian category. And these are very important properties, which in some applications are just automatic because you only work with a class of categories. I mean that, but sometimes you have constructions where you start from the leading category, define something new, like categories of induced modules, this is a typical thing, which are no longer abelian. Then there's a question, what type of limits exist, how general, how good is your new category? And for that, yeah. Oh, I introduced this notion of a zigzag last on Tuesday. So if you have an object x and x prime, and then there are x1, x2, x3, and so on, up to, well, this would be x0, which is x, and then there is some xn, which is x prime. And then you say, if such non-zero, such morphisms exist here, then you say they are path connected, x and x prime are path connected, and pi 0 is the set of path components. And the statement was about the number of path components.
Oh,
So if I have such a thing in some category C, and I have another category C prime, which is equivalent to it, that means that for any object here, I will have at least one object x2, say prime, which is isomorphic to it. And you have this for all of those. So just composing with these isomorphisms, when you have a path in C, you get a path in C prime and the other way around. So number of path components is a property not of just a single category, but of an equivalent class of category. If the noise is not too much for the big one too.
I don't think that.
Okay, yeah. And the micro is really good. Okay, I think we can continue. It's an important question whether all limits or maybe all finite limits exist for a category, but it could be hard to know this for a given concrete category. Fortunately, as you will see, one does not have to look at all limits, but only on the class. First, relevant terminology we will need for that. We say that no, it's more remark. Remember that any set, and I'll write a Roman I, not script. Is a category where we simply say that, well, let me call it CI, where HOM CI just consists of the identity morphisms for all elements of I. And then that means that we can in particular look at diagrams of shape I, well, of shape CI to be precise, but one just says I. Well, what is this? The morphisms are trivial, so since we're talking about functors, so they have to be mapped to identities, have to be mapped to identities, so there is no freedom in that. So the only thing that is real information is what happens to the objects, and then this is nothing. This is just the same as a family. Xi, where I is an element of the set I of objects in C. Maybe I write E not to mix it up with the. Now we can in particular look at limits of such diagram. That's not in the terminology. For I, a set, we say that the co-limit, but the limit, and then analogously co-limit over or off, often says over an I-shaped diagram. Let's call it again X. The X is such a family now. Is called the product, or if one wants to be very clear, it's a categorical product. It was not to mix it up with other notions of product. Over the family Xi, and analogously the co-limit over such a diagram is called the co-product over xi. And these limits are important, so one introduces also corresponding special notation. One writes the product over a family xi as a product. As product over I and I x xi, and products over xi by product sign turned up and down. And what does this mean for the diagrams? If I really draw them as diagrams, well, we have our axis, the x. Assume we have a discrete set for simplicity. Then otherwise I have hard time to draw things. Then we have the product, and then there will be morphisms to all of these, satisfying compatibility. And similarly, if I have look at the co-product, there will be morphisms from all. Let me give you an example. Examples. Let's first take C to be the category of sets and maps. Then the product. Well, for sets, you expect it's something you know, and indeed it's just a Cartesian product. Or do it? This looks like an X, but this should be a Cartesian product. Whereas together with, we need these morphisms. These are just the projections to the corresponding vector. And the co-product is the disjoint union. It's an X, of course. Yeah. With the corresponding maps here being the inclusion maps. In the second example, take E to be the category of groups and group homomorphisms. Then the product is again the Cartesian product. The Cartesian product of the underlying sets together with the natural group structure on it. Whereas the co-product is the free product of groups. So in general, product is something more finite than co-product. Maybe I mentioned this already last time, but here at this point it's worth saying explicitly. Disjoint union means that an element of the disjoint union of sets is a pair consisting of a set and an index such that natural inclusion holds. It's one important product and co-products. It's one important a special case of limits. And there is another important special case that I wanted to make a statement here. Maybe. Here as a possible exercise, this is just a claim I made. A check that they have to. Well, I told you what these maps are, but then you have to check that they have to, together with this collection of maps, you have this universal property, and that's nice exercise to check. No, later. Here. So another special case is obtained when I just have two objects in my category I and two parallel non-identity morphisms. They are always the identity morphism, and parallel means in the same direction. So this would be another example, say. I have two objects and two parallel non-identity morphisms. So my diagram will look like I have an object X in C and an object Y in C and two morphisms F and G between them. And in this case, we have the following terminology. The limit of such a diagram, provided it exists. And remember, then it's unique up to some obvious isomorphism, is called the equalizer of the morphisms F and G, or of the pair FG, if you like. And analogously, the co-limit is called the co-equalizer. So and we denote this then also by just writing equalizer of F and G, respectively co-equalizer of F and G. A remark. If we have such a co-equalizer diagram, what does this look like? Well, we have X and F and G to Y, and then we have the co-equalizer. Analogously for the equalizer, that means in particularly have morphism in this direction, such that this commutes, and then there is this universality property. And in this situation, we also talk about the co-equalizer diagram when we have parallel morphisms f and g to y, and then a morphism, let's call it p to z, with p after f equals p after g. And what is the universal property? That for any, let's call it Q now, from Y to W, another, or Z prime if you like, such that G composed with F equals Q composed with F equals Q composed with G. There exists uniquely Q hat, say, from Z to W, such that if I compose Q hat with P, then I get P. It is just a repetition of the inverse property, and so one abbreviates this this picture by this one. So G P after G. Let me see. Would be, well. If I take a morphism here and compose them, then they will have this property here. And a remark about another possibility to characterize this following. If C admits all coproducts, so if all the co-limits without the special type of their coproducts exist, then we have a co-equalizer diagram. E star is a co-equalizer diagram. If and only if the following diagram X coproduct with itself, and then the pair F and G to Y, and here I take the natural morphism to X. If this is push out diagram. So if I have X, Y, and Z, then there is a push out of this particular form. And again, as an example, for equalizers and co-equalizers, let's take the category of sets. in this case, the equalizer of two parallel morphisms f and g, say from x to y, is that it's a set, and it's well, it exists, and it's the set of all those elements of x such that f of x equals g of x. So this is a subset. And the co-equalizer of f and g is the object y. But the set y divided by the equivalence relation, which simply says that f of x as an element in y, we have that let me see what x, that doesn't make sense. It should be equality. This is a quotient quotient. And when I was starting to read this, I wanted to use the word quotient object, but that we have not defined. But here for sets, we know what. So this is again a claim exercise. Would we check details? So in particular, what are these are limits and co-limits, so they are not just objects in sets, but that's together with natural transformations. So the next step will be a particular example of a co-equalizer, which is of a lot of interest in various applications. What is this?
Just click the blue button.
No. Ah, this disappears. No. Let me go here. Everyone has to, yeah. No.
Yes, yeah.
Maybe you can take the
Well, the question is whether the people on Zoom see it or not. Probably not. Okay. Can you extend it again?
This is from TV or from the computer?
From computer. What does it say?
Yeah, this pop-up must come from the TV or come from the PC. I think it's it's TV. It's TV, not the.
那个有空气都是 TV 的话，容器啊，
Sounds digital.
I think we need
让它能够容器。
那边 control of the TV.
I think this is what is the control for it?
再把这个设人，它那个。
啊。
Thank you very much. So one example, one very specific example of co-equalizer and actually also the equalizer version of it, which in a more general situation than what we consider now will be of much relevance in applications, some of the applications I have in mind to present. And this will take a little time to define, because I want to use the opportunity also to introduce more aspects of graphical calculus. So we assume from now on for some time that R is a unital ring. And I denote the unit just by 1. And then remember that a last R module is a pair M row, where M is an abelian group. And a row is a map from R cross M to M that is compatible with this is called the action of R on M. That is compatible with the various structures. I don't maybe write down all of it. So first of all, it's compatible with the abelian group structure that I don't write down, but then maybe I write down. I have a product, which I just do not indicate by any symbol here, and this maybe I should try this here. I have an element R in R and an element N in M. One also writes it as R dot M. And there are some properties which I don't write down, which are rather obvious, and then R prime applied to M is the same as first applying R prime to M. So I get another element in capital M and then active R. And then the unit acts trivially. Analogously, we define the right R module. If it's not obvious to you, then it's an exercise to formulate it. And then we define an R bi module. This is a triple, M rho and say sigma, where M together with rho is a left R module. And M together with sigma is a right R module. And the left action and right action are compatible, namely, if I compose rho times the identity on M with sigma, then it's the same as if I compose rho with on R, identity on R for sigma. And what's this? A morphism of left modules and then analogously of right modules. And the bi module is I take left modules and call them M rho and M prime rho prime. this is a homomorphism of abelian groups M prime, which is again compatible with the action. So rho prime composed with identity on R times F is the same as F composed with rho. Instead of action, sometimes one also says scalar multiplication, because, well, you can do, well, this in a sense just is a generalization of the tensor product over a field describing multiplication in vector spaces with elements of the underlying field. And examples, well, I don't write that. If I take R to be the integers, then the R modules are just the abelian groups. This is essentially a reminder. You most probably have seen this. And I haven't yet come to a co-equalizer, but before that, I continue with an element of graphical calculus. Now, the graphical calculus that I mentioned was for categories. Here we can of course formulate this in terms of categories, but I will not do this formally. But think that it's rather obvious how that would be done, and we will do this again and again during the lecture. So we want I want to have a graphical description of this row. R and M would be objects, say the category of sets in full generality. Take R and M, and then a row. I would, this is from R cross M, which I just indicate by putting them next to each other, and that this is a sensible notion or a sensible way to do things. We will understand when we talk about monoidal categories later on, and then this should go to M. So the row is just, I would draw it like that, for example. And then the representation property here will be the following. It says that if I take the product of two elements of R, which I just denote like that. So I just write here the ring itself and mean that just taking any element of it, this will make sense. And then I act, it is the same as first acting with this factor and then acting with the other. And this is a representation property, and I could also draw this, but then I would have to use a notation for the number one. And at the moment, I don't want to do that. But this property here, let me see. I haven't done this, but I can. I should maybe. So for a bimodule, I have an action rho and an from the left, and action sigma from the right. And the formula here says that it doesn't matter whether I first act on the left and then on the right, or go the other way around. And then finally, the morphism property says that if I have now an M and an M prime, and homomorphism of abelian groups between them, then I get the same map if I, let me see in which direction we have done it. I act after, no, on the right hand side, if I first act with rho and then apply F, or I first apply F and then apply rho prime. And yeah. Before coming to the main statement in this context, I mentioned the following lemma. Let R and S be rings, and phi a ring morphism between them. Unital rings, but unital is not important here. Do without it, and let M rho be an R module. Then, looking at the composition of the following map, we start with R cross M, then take phi times the identity on M. So we get to S cross M, and no, not R module, S module. And then use rho to get to M. So then we get something from R cross M to M. Then this turns abelian group M into an R module. And we denote this by phi star applied to. And also, if we look at the map, underlying map of abelian groups, underlying morphism M to N of S modules, yields analogously map between the corresponding R modules. And you can combine, well, these have further properties such that if you look at the category of R modules as objects and module morphisms as morphisms, then we actually have a functor we call phi star from S mod to R mod. And an exercise will be check that we really get properties of the of this, and we call this functor also the restriction functor. Or also restriction of scalars. And now I can come to use the concept of co-equalizer to do something with these structures. Example for a co-equalizer. The tensor product over R tensor product symbol with index R, or well, one says tensor product over R, and it would make more sense to draw it like that. But then if you use this in formula, sometimes it's the more common notation of bimodules over a ring R. R is a ring as before, is the co-equalizer so maybe I write it like that. Give these names M and N of two R modules M and N with corresponding actions is the co-equalizer of the. Remember, we need two parallel morphisms, and they are from N cross R cross N to N cross N, where here well, with one of them, I use the representation on M times the identity on N, and on the other one, I take the identity on N times the representation on N. Sometimes this is also called the relative tensor product, to distinguish it from the tensor product over, well, in the case of fields and vector spaces, to the tensor product of over the field. In case of representation of algebras rather than modules over rings. And well, in the first place, what you get if you look at the definitions is taking the co-equalizer here will give you an abelian group. You take the co-limit in the category of abelian groups, but then M is an A bimodule, and N is an A bimodule. Let's indicate it like that. So via the co-equalizer, you take care of these actions. That's, remember the picture that I had here on. Well, what you effectively do is, maybe I should draw this again. You have M and N, and your two maps that you are looking at are this one, and you take the co-equalizer. So what you use for this is the right action on M and the left action on N. I didn't write this here, so let me see. I have bimodules. I should have written this as M rho sigma and N rho sigma prime, and then here I have indeed sigma. So I should call this sigma or sigma M. And here I have rho prime in this notation. And what I'm left with is rho and sigma prime. So these actions that I have here, so there are clearly a left action naturally on not only here, but on then also on the equalizer. and the right action, and it's also easy to check the commute. So what you get is again a binomial. In between, I was talking about algebras. There's no A otherwise. Yeah. Okay. Thank you. And this is a good point for having a break, except what I already said, but maybe not clearly enough. So you can this has a version where instead of rings, I take associative algebras. Instead of the product of building groups, I take the tensor product of vector spaces over the underlying field, and then I get a tensor product of A binomials. That actually will we will generalize very directly to the situation where we are not in this particular case. We are in the algebra situation. We deal with vector spaces, but where we deal with objects in some arbitrary monoid. Okay, that's a great one.
你就提前开，提前开，我提前要开，提前要开啊。那提前是多长时间呢？我出去的时候就说几天，就快了，已经开了，已经开了。1、2、3，是还已经开了。我主要是觉得他们知道我们才要，或者知道他们才要。但是，但是没有任何问题，我单纯的因为我个人认为。很大的好是革命的成果。你还有感觉？你觉得感觉更好还是真的是？我问了很多人，没什么，我没干嘛。2点到头。第二种手不管用，就是你手上跳一下，然后看到面刷一下，就直接就刷出来。对，但是现在中国虽然挺好。说很不幸，我在美国无所谓。
Then we can continue. You could ask the question, why co-equalizer, why not equalizer? Well, that is what we call the tensor product. But we could also just decide to say, let's use the equalizer. And then we get maybe something interesting also. This works at least if we are now in a linear context where we deal with algebras over some field. So A algebra, remember K is a field always, and I will usually assume that it's algebraically closed. And then if you look at A star, where star is the dual in the vector space sense, is naturally K co-algebra. Where I assume you have some idea what co-algebra means. We will introduce this in the context of monoidal categories formally later anyhow. And then we let M sigma, where sigma goes from M tensor over K A to M, be right A module, defined in complete analogy with the case of rings. Then we see that this becomes right A star co-module via, well, co-module means we need a morphism from our vector space M to M tensor A star. And this, I call this delta. So if I have any element M in M, I map this to sum over I, M AI acting from the right on M. So this is a right action, which I have called sigma here, and again denoted by a dot, a tensor product over KAI, where, and I made a mistake here, I should say finite dimensional, in order for the next thing, for the sum to make sense, where the AIs are a basis of A, and the A upper I are the corresponding dual basis of the dual vector space. Of course, I can do the same for left modules, and I can do it for bimodules, and then we can define not a tensor product over A, but a tensor product under A. Of A bimodules. As the equalizer of, let's call them x1 and x2. So x1 tensor under A x2 is the equalizer of the diagram. I indicate it like that, where I have the tensor product over K, and then I have two parallel maps to x1 tensor A, tensor x2 over K, where, not A, but A star, and then I have here delta for x1, tensor over K with the identity on x2, and the identity on x1, tensor over K with delta for x2, where I now, because I'm running out of letters, have used delta for the right a co-module structure on X2, and here also for the left a co-module structure on X1 and here on X2. And this turns out to define another tensor product on the category of A modules, which now for the on the category of A modules, the answer by A itself, which is naturally via the product by module. This is in particular the identity for the tensor product, and in this case, A star is the identity. And it turns out that not only tensor product over A, but also this tensor product under A here are interesting in more general context of other monolithic categories. And the last part of section 1.6, I have an important result, which is the one I was looking for previously. I didn't remember that I stated earlier. Now we could have stated this earlier. There is a statement that if C admits all products of families of objects in C exist, and all equalizers. So for any two parallel maps, the equalizer exists. Then it follows that together C is complete. So actually, if these particular limits exist, then all limits exist. And that's of course very convenient if you want to use statements using that all limits exist. For category, it's enough to know that these exist, and then of course there is a co-version of that also. And I will say a few words about the proof, but I have to admit that I had to look this up by myself for including this into the course. I had to follow carefully now my notes because I have not done this independently. So the idea is, of course, it's enough to prove one of the statements. The other one you get by looking at the opposite category. Assume we have a complete category. So in particular X from small category to C, be a diagram that has a limit. It's provided as lim of X, so that exists, and then one shows that the limit can actually be written as the equalizer of the following parallel morphisms. I take the product over I, and I have two natural transformations here to the product where I take the product over all maps from I to J, and where I and J are in I. I call these two here lambda and mu. So these are natural transformations. For any given f, they have components which go from product over the xi to some given x of j. And they are defined as follows. Lambda f. We start, say, from k in I, product over x of k. Then I take the projection, which by definition of the product exists, projection number I to x of I. And then I take, given an f, my x of f, which will go to x of j. And uf is instead obtained by directly taking the projection with respect to projection to the chase component. So I either go directly to the factor x of j, or I first go to x of I and then use f to come to x of j. And then I take the equalizer of those, and then I want to show that this indeed gives me the limit. So what one has to show is that it's a cone that's not hard, but then it has the universal property, and that's of course quite a bit harder. This gives you one, well, starting from, well, no, let me see. Once I know that this is an equality, then I have both directions of the statement. And just as an example on how to make use of that or make non-use of that, the category of sets, the category of topological spaces, and the category of modules over some ring R are all complete and co-complete. And you show this by showing that they admit all products, co-products, equalizers, and co-equalizers. And if you look at the category of manifolds, then this is neither complete nor co-complete. And in particular, not all pullbacks exist. Remember, pullbacks are particular limits. And actually, I haven't looked that up, but there is a there's a rather nice example for that. And this statement here, I will implicitly use later on. So now we finished with 1.6, which is relatively long. 1.7 is also not short, but it's largely a collection of definitions. So this is about now abelian and additive and abelian categories. And I have introduced almost everything I need for defining them, but there is little bit more, which is the following. And so additive categories, and we'll talk about additive categories and about abelian categories. Abelian is a specialization of additive, actually. I start with another definition. A terminal object in a category C is an object that's denoted by Z, last letter of the alphabet of C, such that for every Y in C, Y in the category, there is precisely one morphism. Which ends up in Z. Dually, if I do this for the opposite category, then in the original category, I get the notion of initial object. Instead of terminal, sometimes it says final object, but I will use this. This is an object. First letter of the alphabet is A, but I use A for algebra. So I chose here just X. That for every Y in C is precisely one morphism from X to C. Let me see. Yes, from X to Y. And the zero object is an object which is both terminal and initial. And one can show that this has in common with objects defined by universal properties, that assuming they exist, then they are unique up to unique isomorphism. So therefore, we can talk about the terminal object and the initial object of a category. And we can also describe the terminal object as the empty product and the initial one as the empty co-product. So we take a product or co-product over a set which is just the empty set. That is sometimes a nice thing. These examples, that fits here. As usual, we consider the category of sets. What could be an initial object in the category set, the set, such that to any other set there is a unique map. If you think about it, this has to be the empty set. And the terminal, then any map to that set, there must be precisely one way to map to that set, so that set should have precisely one element. So let me denote this again by some symbol. One element set is the terminal object. If you take vector spaces over some field, then it's clear that the zero-dimensional vector space is both terminal and initial, so zero object. And another category that we have dealt with here, for example, is, well, not directly, but objects of it.
Why is empty set is not terminalis?
This one?
Why is empty set is not terminal?
Why the empty set is not terminal? Let me see. Because if you have an arbitrary set, then let me see.
It's more like before.
There is no map. Yes, there is no map to the end, because the map has to map every element to something. Unitary rings, third example. In this case, the integers are initial, and again, the one element set is terminal. Then, once we have these, we can define further. Well, once you have a zero object, and consider a morphism between two objects of Y, then we say the kernel denoted by ker of F is the pullback obtained by looking at, well, we have our X F to Y, then we have a zero object. There is a precisely one morphism here, and then we can take the pullback. Provided it exists. And the co-kernel of F is the push out. In that case, we have, besides F, we have a map, a unique map from X to the zero object, and then we can form the push out again, provided it exists. So now we come to the notion we have in the title of the subsection. Maybe I write this here. We can remember notions of zero object. Definition. An additive category this is a category such that first of all, every morphism set Hom xy for any objects x and y has the structure of an abelian group. And composition is compatible with that, so it's that linear. And all finite products and co-product equals. So here we don't need those concepts, but I define this here because now once we have that, we can easily say an abelian category. This is an additive category. Such that in addition, every morphism has a kernel and a co-kernel. So these push-outs and pullbacks exist. Then let's assume that f from x to y is a monomorphism. The square given by x is 0. So remember, if we say kernel and co-kernel, we assume that there exists a 0 object. So we have this co-kernel. Then this is a pullback. Remember, by definition of the co-kernel is a push out. But now we look at this part and say that this is a pullback diagram. And you could formulate this by saying every monomorphism is the kernel of its co-kernel. And if instead we have an epimorphism, then surely the diagram where we have the kernel which by definition is a pullback is a push out. Every epimorphism is the co-kernel of its kernel. As usual, you find this, of course, in all textbooks. So, in particular in MacLean, and I instead of telling you precisely where in MacLean there is an article by Gu, which I will include in the list, where which has an appendix giving many of these definitions and saying precisely where in MacLean they are. And yeah, one property. On the side, we can formulate the following lemma. Let's see the additive. Oh, I forgot to mention, I will not use it, but you will occasionally see this in the literature. If you have only this first property here, you call the category also pre-additive. And if you have an additive category where you have only this first property here, you call it pre-abelian. So let's see the additive. And then it actually follows that C has a zero object. So when we say here kernel and co-kernel, we need in particular that a zero object exists, but it already exists because we require additive. And also finite products and finite co-products coincide. Or sometimes one calls them byproducts. And an example, or rather not a counter example, not additive are the category set, group, and unitary rings. Just remember what I said about the initial and final objects in set and in unitary rings. They do not coincide, so there is no zero object. And in group, we have seen the products and co-products are different.
Can you repeat? You said additive implies existence of an object.
Additive implies that there is a zero object.
So, because you use the existence of the object as a definition.
No. This looks like as if in this first requirement of pre-abelian, I have to require existence of zero object, but actually I don't have because it's already included here. So many interesting categories are not additive. Then there are many interesting categories which are additive but not abelian. And this is, for example, the category of Hilbert spaces, which otherwise for a long time at least I will not talk about. Then to get a very simple example, even though you would not use this. For anything I would find interesting, I guess, but to just look at even dimensional vector spaces. And more interesting is free abelian groups. So the category of groups is not abelian, but the category of abelian groups is abelian. That's where the terminology comes from. But the category of free abelian groups is not. But it's additive. But now an example, which is an example. R mod for any ring R and vector spaces over K for any field K are abelian. And in particular for these, I don't write it down. The kernel is what you define as kernel in terms of the subset that is mapped to the zero in the ring, respectively, in the vector.
What do you mean by free?
Free-wheeling group. Oh, it's a group on. Let me see. My naive answer would not be correct. So you have generators. Yeah, just some number of generators, and their product. For the product, order does not matter, but otherwise you have no further relation.
The power of the group.
I don't know. I have not looked this up, and I never had to do it. But that's what I think, what I would guess. Just any two different generators commute, and then there are no further relations. And this is, of course, a subset of subcategory of the category of all of these groups. Because you can have relations. Then just two more definitions, and then we essentially finish for today, I guess. Definition. First, a constant morphism is a morphism, say, from X to Y, such that for all G and H, which are morphisms to X, say from W, we have the identity F composed with G equals F composed with H. And purely a co-constant morphism again, say from X to Y, is a morphism such that for all G and H, which now go from Y to something, let's say, we have that in the other order G composed with F equals H composed with F. And a zero morphism is a morphism which is both constant and co-constant. But multiplying this with number zero, if you have numbers, makes all other numbers. Zero times anything is zero independently of what that anything is. For that constant. And remark. In the definition of terminal, initial, and zero object, we talk about unique morphisms that should exist, and these unique morphisms are of this type. These are constant, respectively. No, for terminal, they are co-constant. It goes to some set and constant and zero morphisms. So whenever one talks about a zero morphism, it's something which morally is this unique morphism, zero object, even though we don't have always to talk about zero object. And now, an important concept, which we will, concepts which we use very often, and which is one of the reasons why we are often interested in abelian categories. In an abelian category, we can define the following subobject of an object X is a pair, let's say S and I, consisting of an object in C and a morphism that is a monomorphism. I from S to X, and dually to that, no, I need more space. I just continue here. No, let me write this again. Then a quotient object yes, of an object X and C is again a pair. We call it Q now, X and R. Where Q is an object. And an epimorphism R from Q to X, from X to Q. And sometimes one also uses the term subquotient object. It's an object which is a quotient object of a subobject. Of X. Okay. I will stop here, and then next week we continue with a few statements about abelian categories and related things, and in particular we introduced the notion of exactness of a functor, which we can do in abelian categories, and this is yet another reason why abelian categories are important. And let me also mention that very precisely, like in many other situations, the Q here is determined up to a certain equivalence relation. So instead of defining this as a pair of object and morphism, one can also define it as an equivalence class of such pairs. And in some situations, one has to be careful about that, but I will not go into that at all. Okay, thank you for today. And now, again, someone has helped me to get this recording done. So I first have to leave the Zoom.